Hello and welcome to Aditya classes, and this is Manish Tamar, and we are studying sequencing these days. So we discussed what all we are going to have a look at in the sessions to come. So we'll be having a look at how to sequence n jobs on 2 machines, n jobs on 3 machines, n jobs on m machines. When the sequence is fixed 1, 2, 3, 4, 5, or it could be anything 3, 4, 5, 2, 1, but it will be same for all. So if the sequence is fixed, then how do we sequence n jobs on 2 machines? This is what we will be seeing today. This is what we will be studying, sequencing n jobs on 2 machines using Johnson's rule. So let us prepare some dummy question, and then we'll work on that question. So here is our question. What is this question? That we have 7 tasks at hand. Task 1, 2, 3, 4, 5, 6 and 7. Now these tasks pass through machine A and machine B. The sequence will strictly be A and B. First you go to A, then you go to B. Now we need to prepare a schedule such that it minimizes waiting times for machines and elapsed time. So what is the waiting time for machines? Suppose you have done some work on machine A, and then during this time machine B was waiting. Suppose you need 3 minutes on A and you need 5 minutes on B. So what happens is, you start with A, 0 to 3 minutes, you will work on A. So we are taking a very simple case where I need machine A, machine B, task 1 arrives, machine A, it needs 3 minutes and 5 minutes. So how it will process is, when task A comes, it is mounted on machine A and it finishes in 3. Then it is mounted on B and it finishes by 8. So 0 to 3 because it was 3 minutes. Processing on B starts at 3, it takes 5 minutes and we finish it at 8. Now if we look very carefully, what is waiting time for machines? Was there any waiting time for A? Waiting time, or rather we could call it idle time. Was there any idle time for A? There was no idle time for A. As soon as we started the workshop, we started the service station, A was in operation. But what about B? B got into operation only at 3. So for these 3 minutes, B was sitting idle. B was waiting for some task to come. So this 3 minutes becomes waiting time for B. In a sense, it is also idle time for B, because B is sitting idle waiting for the job to be mounted. So for B, the waiting time is 3, because workshop started at 0, B started at 3. So this 3 minutes was waiting time, and in a sense it was sitting idle also. So what is the idle time for B? Idle time for B becomes 3 minutes. From 3 to 8, when is the workshop shut? You start at 0, you shut at 8, because we processed completely. So you start at 0, you finish at 8, complete time is 8. Of those 8, from 3 to 8 B was working. So what was the time when it was idle? It was idle from 0 to 3. From 0 to 8, B has been working, B was engaged. So B was not idle. But prior to this 3, B was idle. So idle time for B is 3. What about the idle time for A? As far as A is concerned, there was no waiting time. As soon as the processing started, A was into action. But what about idle time? A got free at 3 minutes and the workshop was shut at 8 minutes. Workshop was shut at 8 minutes. So from 3 to 8, A was sitting idle. So this is how we check idle times for all the machines if they were idle. Why do we check idle times? Because so that we can work upon improving their idle time, minimizing their idle time. We could go for sequencing, we could go for shifts in such a way that these idle times are minimized. Why are my machines sitting idle? Even if my machines are sitting idle and my service station is open, there are lighting expenses. There are other expenses related with keeping the service station open. So try to minimize the idle time so that I can change my shift timings. So this is why we keep a check on idle times. What is the elapsed time? Elapsed time is you start at 0 and you shut your service station at 8. In the morning you started at 0, in the evening you shut at 8. This is the elapsed time. So what will be the elapsed time? Elapsed time will be when the processing start to when the processing ends for all jobs. This is elapsed time. We saw how can we find out idle times. Idle times are for what time we were sitting idle, B was sitting idle for 3. For what times we were sitting idle, B was not sitting idle, but A was sitting idle for 5. So in this way, when we see this question, we will see how do we find out these idle times and elapsed times. So elapsed time is from starting of first job to ending of last job on last machine. Starting of first job on first machine to ending of last job on last machine. This is my elapsed time. Right? So, let us start with our sequencing algorithm. Now, what does this algorithm suggest is that there are 7 jobs that need to be sequenced. So, let me make a matrix, a vector of 7, 1, 2, 3, 4, 5, 6 and 7. So, this is a matrix of 1 by 7. This is where I will be putting my sequenced jobs. Now, what is the rule of sequencing? A very simple rule. The rule would be find the shortest time. Find the shortest time in complete list. Then take your decision. If the shortest time is on machine A, then sequence the job to start of queue. This is my queue. Sequence the job to start of queue. This is my start of queue and this is my end of queue. If you happen to find the shortest time on machine A, sequence the job to the task to start of queue. If the shortest time is on machine B, sequence it to the end of the queue. As simple as that. Very simple rule. Look for the shortest time. If it happens to be on the machine A, sequence the task on starting of the queue. If it happens to be on the machine B, sequence it at the end. A, go to start. If the shortest time is on B, go to end. As simple as that. Now, there will be certain ties also. You might happen to find 5 minutes, 5 minutes, 5 minutes at 2-3 occasions. So, when that tie comes, we will see that that is not actually a tie. If we go by the logic, there is no tie. And if there is a complete tie where everything is same, then you can go with random, anything. If the jobs are completely similar, then you can go with either. Fine. So, let us start with our sequencing task. What are the rules? Find the smallest time, shortest time. If it happens to be in A, go to the start of the queue. If it happens to be in B, go to the end of the queue. Where is our shortest time? Let us scan through it. Where do we see the shortest time? If we scan through the complete matrix, we see that there is a 20, there is a 25, then there is another 20, so there are 2 20s, then there is a 15. So, this 15 becomes the shortest time in complete table, complete data. This is my shortest time. And where is the shortest time, in A or B? If it is in A, go to start. If it is in B, go to end. It happens to be in A. So, this task is sequenced to the start of the queue. This task is going to the start of the queue. Done. Task 6 is sequenced. Okay, so this is good. Task 6 is done. Now, if I remove task 6, what is the shortest time? We scanned through the table, there was a 20, 25, 20, 30. So, who is the shortest? 20 is the shortest. And incidentally, the 20 is visible at 2 places. This is a tie. And again, incidentally, both these 20s happen to be in A. So, both these tasks will run for the starting of the job. Now, imagine, let me minimize this question. What are the jobs? 1 and 4. 1, 4. A, B. 20, 20. And then there is a 25 and 30. Right? Now, suppose my question was only this much. So, my sequencing queue would have been only this much. Now, I have two rules. If the shortest period happens to be in machine A, go to start. If it happens to be in B, go to end. If I look here, my shortest period is in machine A, but it happens to be at 2 places. So, I am not able to take a decision. If I am not able to take a decision from here, leave it. I will take my decision from elsewhere. What is that elsewhere? It is machine B. Which decision would I make? Which is the shortest period? 25. Where does this shortest period take me? To the end of the queue, because it happens to be in machine B. Remember, when the shortest period is in machine B, you go to the end of the queue. A was giving me no decision. I was stuck with 2 cells. I knew that I have to go into these 2 cells, but I was not clear. Where is 1 and where is 4? When I move to machine B, I see that shortest time is in job 1. And where does shortest time in B takes me? To the end of queue. So, who is going to the end of queue? 1. Who is coming to the start of queue? Obviously, when only 4 is remaining, it will come here. Now, if I try to superimpose this, what were these 2 cells? These 2 cells were from here. Why from here? Because technically my shortest time was 20. It was supposed to go in start. One of these will get this cell. Whosoever loses will get this cell. So, I had 2 shortest times. Those both shortest times were in A. So, I run to start of the queue. One will get this cell, the other will get remaining cell. So, this is why we are taking these 2 cells. And how do we solve this tie? Here we saw. Now, we will not be taking these kind of explanations everywhere. I assume we have a very good idea about how to solve a tie. How do we solve a tie? Who are the 2 eligible jobs? 2 eligible jobs are job 1 and job 4. So, one is coming here and another one is coming here. Why are they coming here? Because they both happen to be at machine A. So, if a shortest time is in machine A, you go to start. So, one will get this spot, one will get this spot. These are the 2 spots that I have reserved for these. But I am not able to decide who is coming here, 1 or 4, 4 or 1. I am not able to decide. So, I move to B. In B, I check who is the shortest. Who is the shortest? First is the shortest. In B, the shortest takes you to the end of the queue. So, if this is my limited queue, who is going to the end? The one with shortest P. Who is going to the start? The one with longest P, or the left one, the remaining one. Are we clear? Why we went for 6, 4, 1? 6 was very much clear. It was shortest in A. You go to start. For next, when I saw, I had 2 20s and both 20s happened to be in A. Now, because both were in A, there was a tie. To resolve that tie, what I did was, I moved to B. The rule for B is the shortest takes you to the end. The shortest was 25, it takes me to the end. But where? To the end of the queue at the moment. At the moment, this is my queue. Why is this my queue? Because there are 2 shortests in A they have occupied these two cells. They have to occupy these two cells. But which one gets what? We decided upon B. This will be clear. We'll take more examples. No need to worry. So, now what I can say is these two have been completed. Assigned. Now, what is the shortest time? Let me check. I have a 60, then I have a 50. I have a shortest time of 50. Where is that shortest time? It is in machine B. Whenever it happens in machine B, you go to the end of queue. Shortest time is 50, it is in machine B, you go to end of queue, that is this task 7 is going to the end of queue. Now I can say that this has been resolved. Task 7 has been sequenced. In the remaining of the table, what is the shortest? We have a 60, 75, 60. 60 is the shortest. So, I will assign this 60. Where is this 60? This is in B. Whenever shortest time comes in machine B, you go to the end of the queue. Who is going to the end of queue? Job 2, task 2. And now I can remove this task also because I have assigned. Now, what is your shortest time? You have a 75, this 75 is the shortest, and this 75 happens to be in B. So, B takes you to the end of the queue. Who is going to the end of queue? 3. Done with this also. Now, the only task remaining is 5 and the only cell remaining is this. You can put 5 over here. So, this is how we prepare a sequence using Johnson's rules. And the rule is very simple. Check for the shortest time of the eligible jobs, of the remaining jobs. The jobs that have been sequenced are left. The jobs that are remaining now, you take the shortest time from those jobs, and if that shortest time happens to be in A, go to start. If that shortest time happens to be in B, go to the end. Simple, plain. Fine. Now that I have this sequence, I need to find out what is the idle time for each of the machines and what is the elapsed time. Now, we have two machines, so we will make a table and then we will enter values over there. Initially, we had 1, 2, 3, 4, 5, 6, 7, but now according to my calculation, according to Johnson's rule, the sequence should be 6, 4, 1, 5, 3, 2, 7. This should be my sequence. Then we need to monitor idle times and elapsed time. Machine A and machine B. And this column exactly is not required, but we have put it over here just to monitor idle times of B. With a little bit of practice, we can do away with this column. This column is not exactly required. We can find out it without this column also. But because this is our first question, first time we are attempting to find out idle times, we will put a column so that it is mechanized. So, this is idle time for B. This is it. Now, so I have brought that question over here so that it is easy to refer. Now, this is our table. You start and start and end. Start of processing on machine A, end of processing on machine A. Start of processing on machine B, end of processing on machine B, and if at all there is some idle time, we will try to keep a track of that. So, who is going first? We saw our sequence was 6, 4, 1, 5, 3, 2, 7. This sequence seems to be the best one according to Johnson's rule. 6, 4, 1, 5, 3, 2, 7, 6, 4, 1, 5, 3, 2, 7. Now, at this very moment, who is the first one to go into the line? 6. So, 6 can start at this very moment. Without any delay, 6 can start. We see here 6 is over here. It can start. How much time it takes on machine A? 15. So, if you start at this very moment, the processing on machine A for task 6 on machine A takes 15 minutes. 6 on machine A starts at 0, finishes at 15. Now, as soon as it finishes on A, it will move to machine B, right? And how much of processing is required at B? 35. So if you start at 15 plus 35, how much time will it take? 50. At end of 50 minutes, A will be through. Task 6 will be through with A also and B also. 0 to 15 for A, immediately shifts to 15 and at 50 it ends. Was there any idle time? B was sitting idle for 15. These may be minutes, seconds, time, hours, days, whatever it is. So, B was sitting idle for 15, that we can make out. Now, what happens with second case? As soon as job task 6 is removed from A, as soon as you remove task 6 from A and shift it to B, machine A is free, machine A can now engage the next task. What is the next task? It is 4. How much time it is taking? 20 minutes. So, 15 plus 20 it would be 35. Now, task 4 is ready to move to B, but can it move to B? B will be free by 50, that is the catch, because task 6 is being performed on B, task 6 is still continuing on B, though task 4 is ready, task 4 is free, but we cannot start with machine B because machine B will be free at 50. So, what time do I put over here? When can task 4 start? Task 4 is free at 35, but machine B is not free. When is machine B free? It is free at 50, right? So, it is free at 50. Now, task 4 can start on B. Task 4 on B is 30. So, if we start at 50, we will finish it at 80. Very smooth. Now, what happens with 1? 0 to 15, 15 to 35, machine A was engaged. Immediately machine A is available for task 1. Yes, task 4 is waiting for 35 to 50, but we can remove it, unmount it from machine A. We can keep it elsewhere. So, we will keep it elsewhere so that machine A can be utilized. So, machine A will start with processing of task 1. How much time does task 1 take? 20 minutes. So, 35 if you start, you will be free by 55. Now, you are free at 55, task 1 is free at 55, but can it move to machine B? Sorry, machine B will be free at 80 because it is still processing, it is still working with 4. So, in spite of you being free at 55, but you will get machine B only at 80 because it will be free at 80. How much time do I need? One needs it for 25 minutes. So, if I start at 80, I will finish it at 105 minutes, seconds, whatever it is. Now, what about idle time? Machine B was released at 50 and it got engaged at 50. If we have a look at these two times, was there any idle time? Second case, machine B was released at 80 and it got engaged at 80. Is there any idle time? No. What about A? Again, for A also you can see there is no idle time, there is no idle time because A is not waiting. A just finishes with one task and moves to second task. This is it. Now, for A is free at 55. You can start with task 5 at 55. Without worrying how much time will it take, you can start at 55. Now, let me go and check how much time will actually be needed. 120 seconds worth of processing, 120. So, if I take task 5 now, it will cost me 120, making it 55 plus 120, 175. Now, what happens? Task 5 is completed on machine A after 175 minutes. Machine B was free at 105, but now machine B will have to wait for some time. Why wait for some time? Though machine B is idle, but next task is coming at 175. So, here I see that 175. Machine B, processing on machine B for task 5 will start at 175. So, now I can see that if a task is free, but machine is engaged, then you get machine at later time. If machine is free, but task is engaged, then you get machine at later time. So whenever we are moving from one machine to other, you take the later of the times. In this case 50 was more than 35, I went with 50. In this case 80 was more than 55, I went with 80. In this case 175 was more, because the machine is free at 105, but the task is not completed. Task will only be completed at 175. No issues. Now at 175 you get machine, go to machine B, and you need 90 more minutes of processing. So 175 plus 90 would take you to 265 minutes of processing. Is there any waiting time for A? For B, B was free at 105, but now it gets engaged at 175, so there is a waiting time of 70. Is there any waiting time for A? For A, you will see that there are no waiting times. A goes on from one task to another. So A was free at 175, A can come here at 175. Now, how much time does 3 need? 3 needs 80 minutes. So 175 plus 80, how much does it make? 255. So task 3 will be completed on machine A at 255, we can see. Now, when do we start here? I am free at 255, but the machine will be free at 265. So when do I start? Very simple. If I am free but machine is engaged, we'll start when machine is free. If machine is free but, so the whosoever is later will have to wait for it. So I was free at 255, but the machine was free at 265, so I waited. Now my processing will start on B, and task 3 takes 75 minutes of processing on B. So it will make 340. B will be completed at, task 3 on B will be completed at 340. And is there any waiting time? We see there is no waiting time. Now A was free at 255, immediately A asks for next job. Next job is job 2. It needs 90 minutes of processing on A, so it will be free by 345. Now I am free at 345, but machine B was free at 340. So our processing will start at 345. Very simple. The later of the times. 345. And how much time do I need on second machine? 60 more minutes. So that makes it 405 minutes. Is there any waiting time for B? We are checking start and end of B, alternate, previous to this one. So 40 to 345, yes, there is a waiting time of 5. You can keep an eye on A also, there are no waiting times, no worries. Now, when A is free at 345, it calls for job 7. Job 7 can start at 345 and it takes 65 more minutes. So, it will be finished by 410. Now, I am free at 410, B is free at 405. When should our next processing start? Our next processing start at 410. Why? Though B was free, but I was engaged till 410. So, I can start my next further processing only at 410. So, from for this 410, task 7 needs 50 more minutes, taking it to 460. Is there any waiting time? Yes, there is a waiting time of 5 minutes. So, this is our sequence. When I try to sequence these 7 tasks to these 2 machines, n tasks on 2 machines. There could have been 9 machines, 9 tasks, there could have been 14 tasks, there could have been 50 tasks, there could have been n tasks. This will be the method, n tasks on 2 machines. So, this was our first question on n tasks on 2 machines. So, this seems to be a lengthy one. In next questions, in questions to come, we will see that is a very smooth process. It is a very fast process. Yes, now let us remove this thing and then we will see what are the idle times and what is the elapsed time. Right. So, you need to find out idle times and elapsed time. Elapsed time was first task on first machine to last task on last machine. First task on first machine, last task on last machine. So, very simple. Elapsed time is then we need idle time. Idle time will be for A, for B. What is the idle time for A? When did A start? A started at 0. It was busy. From 15 it got free, 15 it got engaged, 35 it got free, engaged 55, 175, 255, 345. So, it was engaged all the time. Engaged up till what time? 410. Now, the elapsed time is 460. So, my workshop, my service station is open for 460. Of those 460, from 0 up to 410, completely A is busy. So, what is the idle time? Complete time is 460. 410, A is engaged. So, I can say that 460 minus 410. So, idle time for A is 50 minutes. Idle time for A is very simple. You just take the elapsed time minus the completion time for last job on A. Last job on A. This is it. Elapsed time is simply, idle time for A is elapsed time minus when A is finished. 460. A got engaged at 0 and we saw it was busy all the time. It was not free idle at any time, and finally it got free at 410 while the shop was still open till 460. So, idle time was 50 minutes. What about idle time for B? We see first is 0 to 15, 15 minutes I was idle, then 50 to 50 I got engaged, no idle time, 80 to 80, no idle time. There was a huge idle time over here, 70, no idle time. There was an idle time of 5 minutes again. Before I started task 2, I was idle for some time. Before I started task 1, I was idle for 15 minutes. Before I started task 1 on B, I was idle for 15. So, this is how I am tracking. And then 340, I was idle. Here again, I was idle. So, what is that idle time for B? It will be 15 plus 75 plus 5 plus 5. So, it makes it 15, 20, 25, 95. This is idle time for P. As simple as that. Fine. Done. Another easy way to find out idle times could be, we just take totals of these. So, if we try to take totals of these, we see that total for A would be 410. Total for A is 410. 460 is my elapsed time. So, of those 460, A is working only for 410. So, obviously, idle becomes 50 minutes. Let us check for B also. For B, it will be 365. So, we were engaged for 460, elapsed is 460, 460 minus 365. So, we can see that the elapsed idle time is very easy to calculate. You could calculate it from table. This was our first question. So, we created this column so that we could track what was the idle time, so that we know what is the meaning of idle time. Meaning of idle time, now I understand that processing or workshop started at 0, but B first got engaged at 15. So, these 15 minutes were idle time. Then we came to this point. B was free at 105, but B got a task at 175. Why did B wait for 70 minutes? Because processing on 5 was still going on. It took a long time for 5 to get free from A. So, in that case, what we did was, we waited for 70 minutes. So, this is what is idle time. This is the idle time when A has finished at 410, but the shop is still open till 460. This is the idle time. This is why we were trying to track it in this way. Otherwise, if you go numerically, idle time is simply the elapsed time minus your processing time. For A, processing time is 110, elapsed time is 460, 460 minus 410, 50 minutes is idle time. For B, processing time is 365 on all machines combined. Elapsed minus your processing gives me idle. So, can I try to write a formula somewhere? Idle is equal to elapsed minus required time. So, that will be my idle time. Elapsed is first task, first machine, last task, last machine. This is my elapsed time. And you subtract the required time and you will get your idle time. So, this was our sequencing of n jobs on 2 machines using Johnson's rules. This was first question. It can be a bit tricky, bit confusing. We'll practice more questions in videos to come, and I do recommend that we go through those questions. Once we are through with at least 2-3 questions, not more, even just 2-3 questions, we'll get a very clean, very crisp, very beautiful concept of what sequencing is using Johnson's rules. So, this was it for our first numerical, first sequencing job of n jobs on 2 machines. We'll continue with more numericals. Please do go through those numericals also to get a clearer picture, clearer concept of all these sequencing tasks, how sequencing is done. And if you have any queries, any suggestions, any recommendations, do leave them in comment section. We'll try to address them as soon as possible. Do like and subscribe our channel. Thanks for watching. Bye-bye. Take care.